Can you see the screen? No.
No, sir. No, sir.
Okay. Okay. This is the previous class where we have left. So this is the input, which is one of the standard test signals. The input will be one of the standard test signals. Like here, either it is a step or a impulse, whatever is your requirement, and output is something like this. Now this is the input, this is output. So this, how to plot this output, that we are going to study here. See, this is a typical response curve for step input. So the value of the step is 5 units. So A is 5. So this is the output response of the system with respect to time. We have to plot this by solving. This is one tentative example given. So this is called as time response curve. This is the input and this is a blue one is output. So with respect to time, how it will perform. See here, when the input given is 5 units, the output gradually increases from 0, and as the time passes, it will try to approach equal to 5, and after say time equal to say 16 seconds, it has reached the input. That is 5 units. See, so before this, whatever you call is transient response. And after this time, whatever you call is called as steady state response. So that means a transient response is output below it reaches the input. And once it reaches the input, and what happens after that, that is called as steady state response. So transient response depend upon the system poles and types, and not on the types of input only. Therefore, sufficient analysis of transient response using step input, steady state response depending on the system dynamics and input qualities. This has to be examined by using different test signals. So here, before coming to this, here you can read that is first order system has only one pole. That is what is written here. Forget pole and all those things that we'll study in the third unit. But first we have to see what is known as order of the system. See, basically because it is not possible to generalize the system. The system may be different, and how the systems are categorized in time response analysis, that is by order of the system. If you see the transfer function of the system, depending on that, you have to categorize that system in zeroth order system, first order system, second order system, or in general higher order system. After second order, third order, fourth order, fifth order, sixth order, they are generally referred as higher order systems because there is practically no limit. So here we concentrate on zeroth order, first order, and second order system only. So zeroth order also is being very simple, is not studied in detail because it is not required. Whereas first order and second order system response is studied in detail. So what is the order of the system? In crude way, I can say it is highest power of S in a transfer function. In general, you can say it is the highest power of S in a given transfer function. This is our transfer function. See here, C of S is generally output, R of S is generally input. So output divided by input is K divided by Ts plus 1. where k and t are constants. Here you can see one s is there, that is s to the power 1. That means it is a first order system. So it is not necessary that order of the system means it can appear in numerator also, denominator also. It is in general. In general, denominator order is generally higher than the numerator order. That you will come to know in the next unit. So why it is so? So generally, what is the maximum order of S in the system is there, that defines the order of the system. So this is called as first order system because highest power of S is 1. S to the power 1 is there. So this is a first order system. So here where K is the gain of the system, K is called as gain of the system, T is called as time constant of the system. T is called as time constant of the system, and this is the standard first order transfer function. So this is a first order transfer function. If it is looks like this, K divided by Ts plus 1. So K means it is one constant which appears in the numerator, and T is along with S. It will always appear along with S, and this T is time constant. It may notification may be different. Instead of K, I will say it as L or say M. So whereas T is time, or sometimes it is referred as tau also. Tau is not the shear stress here. It is time constant of the system. So whatever appears along with the S is called as time constant, and whatever appears in the numerator generally, that is, or some constant, it may be 0.5 also. If it is K is 0.5, it can be written as half also. In that case, half is the gain of the system. Then time constant is a measure of how quickly a first order system responds to unit step input. Higher the time constant of the system, slower will be the response. Higher the value of T, slower will be the response. That means the system will be sluggish. The example of common example of first order system is mercury in glass thermometer. The mercury in glass thermometer is generally taken as a first order system. A spring alone, if you write what is the equation of the spring, what is force equation of the spring, what we have studied, that is K into X. Force is equal to K into X. If you take the Laplace transform of that, F of S is equal to K into X of S. Here it does not contain any S. So the spring is zeroth order system. Whereas a damper, if you take damper is force developed by the damper F is equal to B into dx by dt. So if you take the Laplace transform, F of S is B of S into X of S. So highest power of S in this equation is 1. So the damper is first order system. If you take the inertia component like mass, if you take a mass, then F is equal to M into A. That is F is equal to M into d square x by dt square. If you take a Laplace transform, it becomes F of S is equal to ms square into x of S. So highest power of S in this equation is 2. So the mass becomes a second order system. This is how the order of the system is in general, it is mentioned. So suppose this is a one first order system. This is a first order system whose transfer function is 10 divided by 3s plus 1. So this is a transfer function of the system. G of S is 10 divided by 3s plus 1. So here 10 is the gain of the system and 3 is the time constant in seconds. So this is how it looks like. So similarly, another example, 3 divided by s plus 5. So 3 divided by s plus 5 can be written like this. It has to be brought into a standard form. I will multiply and divide it by 5. So 3 divided by 5 and this becomes 1 upon 5s plus 1. So that means 3 divided by 5 is the gain of the system. That is 0.6. Whereas time constant is 1/5, that is 0.2. So here general first order system is represented like this. R of S is input, K divided by Ts plus 1 in general, and C of S is the output. Now let us subject this first order system to impulse input of magnitude 1 unit, that is unit impulse input. So delta T is equal to 1. So the unit impulse signal we have seen in the previous class. So delta T is equal to 1. Delta T is 1 unit. That means R of delta S, that is delta S becomes 1. See here, R of S, delta S, after taking a Laplace transform, it becomes 1 only. That we have discussed in the previous class. If you want, you can go back to our previous class. See here. Impulse input, you can see here. Delta T is A and delta S is A. If A is 1, then it is 1. So we'll come back to this. Delta S is 1. So I am substituting R of S as 1. So C of S divided by R of S is the transfer function, which is K divided by Ts plus 1. Now R of S, I will take it on this side, so it becomes 1 only. So C of S is K divided by Ts plus 1. This can be written as, rearranged as, I will multiply divide by T, because now you are supposed to take what is known as inverse Laplace transform. In the first unit, we have taken the Laplace transform, and now we have to go reverse. That is, in the Laplace transform, it is already there. You have to take the inverse Laplace. To take the inverse Laplace, you have to bring it into a standard form. So this S, highest power of S, whatever is there, its coefficient should be 1. To make it 1, what I will do is multiply and divide it by a same quantity, that is T. That is coefficient of S. So this becomes Kt divided by S plus 1 upon T. K by T divided by S plus 1 upon T. So now S doesn't have any coefficient. That means it has a coefficient of 1 only. So this is called as bringing into a standard form, because unless you bring into a standard form, you cannot take the inverse Laplace. After that, you have to take the inverse Laplace transform. Just now, see here, this is the inverse Laplace transform of C divided by S plus A. Inverse Laplace, if you write L, then it is a Laplace transform. Inverse Laplace is L raised to minus 1. So this is C divided by S plus A inverse Laplace. This is a standard formula, that is C into e to the power minus AT. Apply this to this. C here is K divided by T. A is 1 upon T. So it is K divided by T into e to the power minus T divided by capital T. See. K divided by T is C and 1 upon T is A. 1 upon T into e to the power minus T. This is what is the inverse Laplace of this equation. Now you have to plot this. So you have to plot the impulse response output. It will be like this. See why it is drooping. If I apply, if K is 3, time constant is 2 units he has supplied to draw the graph. This K may be anything and time constant 2 may be anything. K is 3 means time constant is 2 means this becomes 1.5. So it will start from 1.5 only, because impulse response is 1 unit is applied. So it will start from 1.5. Input is 1, but it will start from 1.5. Then as the time goes up, because the impulse response is, impulse input is applicable only when time t is 0. If it is greater than 0, it becomes 0 only. So naturally the output will gradually go on decreasing in 2 seconds, 4 seconds, 6 seconds, 8 seconds, and say 10 seconds. At 10 seconds, it will become 0. That means even though the input is removed after 0 seconds, the output will continue till approximately 10 seconds in this particular case. So this is what is the impulse response of a first order system. So if you know this graph, so depending on the value of k and depending on the value of t, the nature of the curve always remains same. It is a exponentially decreasing curve. Why decreasing curve? E to the power minus is there. E to the power minus is there. If it is e to the power plus is there, then it is increasing curve. Then the first order system subjected to step input. So step input, that is unit step input, that is value is 1. So R of S in that case is 1 upon S. We can go back to that. See here, step input A by S is there. Here A is 1 unit. So it is 1S, 1 upon S. One upon S. So the transfer function is k divided by Ts plus 1. Same thing. So if I take R of S as 1 upon S, so it has to be multiplied. C of S is into R of S, because C of S divided by R of S is this much. So R of S is 1 upon S, so I will multiply it by 1 upon S. So the output now is k divided by S into Ts plus 1. Then it has to be brought down to a standard form. So what we'll do is we'll use the partial fraction methods. Partial fraction method means in maths you have studied partial fractions. Now in the denominator there is one S term is there, one Ts plus 1 term is there. So I will take that as A upon S first term plus second term B upon Ts plus 1. And you have to evaluate A and B. How to evaluate E and B? Evaluation A and B. So I missed out that how to evaluate. Anyway, I will orally expand and I will modify my PPT and give it to you in the next class, because today I forgot to do that. So what you have to do is, now you have to, what I will write, C of S is k divided by S into Ts plus 1. That is left hand side. So this is a left hand side. That is k divided by S into Ts plus 1. That is value of C of S. That I will write in a partial fraction methods as A divided by S plus B divided by Ts plus 1. Then I will evaluate A and B. How to evaluate A? To evaluate A, you multiply both sides of the equation by denominator of A, that is S, and take that denominator tending to 0, that is S tending to 0, and get the value of A. If you get the value of A, that will be K only. Similarly, to get B, that is this part, multiply both sides of the equation by Ts plus 1. So on the left hand side, only 1 upon S will remain, and second side, it is k into Ts plus 1 upon S and B into Ts plus 1 upon S into Ts plus 1. That means B divided by S will remain. Ts plus 1 cancels. Now you have to take limit, that is denominator of B tending to 0, that is Ts plus 1 tending to 0, means Ts is tending to minus 1 or S is tending to minus 1 upon T. So substitute wherever S is there by minus 1 upon T, then you can get the value of B as KT. Value of B as KT. So this is how it looks like after simplification. Now you have to take the inverse Laplace of this. C of s inverse Laplace is C of t. K as it is, 1 upon s is unit step function. That is 1 only. And this t divided by ts plus 1 becomes e to the power minus t by t. So it will, u of t is 1 because it is a unit step function. So output is C of t is k into 1 minus e to the power minus t by capital T. So if you see this, t by t is 1, then it is 0.632 k. So the plot is like this. The plot is like this. That means after t is equal to time constant of the system, capital T, it will reach 63%. So it is increasing curve. Because this is raised to minus, that means it is a decreasing curve. 1 minus is there. So 1 minus this quantity, as it goes on decreasing, this goes on increasing. So it is an exponential curve like this, and it will reach equal to the input. When k is equal to say 10, it will reach equal to 10, and it goes on like this. So the input may be 10 units, the output will also gradually becomes equal to 10 units. See here in general, if the input is 1 unit, output after t is equal to time constant of the system, it is 63.2%. 2 times the time constant, it will reach equal to 86.5%. 3 times time constant, 95%. 4 times time constant, 98%. 5 times the time constant, 99.3%, almost reached. When t is equal to infinity, when it is infinity, e to the power infinity is 0, then it will reach equal to 1. That means when the input applied is 1, output to reach equal to 1, it will take an infinite time. That means it will never reach. That means it will never reach. See, why this curve is very important is, as I said earlier, the thermometer is a first order system. Mercury in glass, when you were children earlier, when digital thermometers were not there, and you have seen the mercury thermometers when you go to a pediatrician, when you were quite young. That time, if you remember, the pediatrician or a doctor puts the thermometer and waits for 1 minute time. Why he waits for 1 minute time? Why don't he take the reading instantly? Even this digital thermometer which you are there using, when you put the thermometer, reading will not be instantly shown. Then it beeps. When it beeps, then only you have to take the reading. Why it is so? Because most of the thermometers which are commonly used in market has around 10 seconds as a time constant. So time constant capital T is 10 seconds. So if the reading is taken after 10 seconds, it is only 63% of the actual reading. Suppose your body temperature is 100 degree Fahrenheit. If it is 100 degree Fahrenheit, that means after waiting for 10 seconds, it will show only 63 degree Fahrenheit. If you wait for 20 seconds, it will show 86 degree Fahrenheit. If you wait for 30 seconds, it will show you 95 degree Fahrenheit. So on, after 5 times time constant, that is after 50 seconds, the temperature shown by the thermometer is 99.3 degree Fahrenheit. That is approximately your body temperature at present, which is, say, I have taken an example of 100 degree Fahrenheit. So that means the doctor has to wait minimum 5 times the time constant. If the time constant of the thermometer is 10 seconds, he has to wait for at least 50 seconds before he takes the reading. And longer his wait, better the reading will be. But he cannot wait for infinite amount of time. He has to see other patients also. So naturally what happens is, he roughly waits for 1 minute time. 1 minute is more than 5 times the time constant. So after he takes the reading. So any thermometer, any device generally has certain time constant. Higher the time constant, more sluggish the system is. Take the example here. Instead of your time constant is 10 seconds, if it is 30 seconds, that means you have to wait for 5 times the time constant to take the reading. That is 30 into 5, 150 seconds. So approximately 3 minutes, 2.5 minutes you have to wait before you take the reading. So generally, the electronic thermometer will are faster responding, basically because their time constant is smaller. Whereas the mechanical thermometers, that is alcohol in glass or mercury in glass thermometer, has a higher time constant and they are sluggish. So why it is also important is, depending on this analysis, you decide which device is used for measurement. Now, if you are taking the body temperature or say water temperature, so in our metrology lab or measurement lab, you have done the temperature measurement by using thermocouple and thermometer, correct? You might have noticed you have to wait longer duration for temperature to stabilize in a thermometer, whereas the thermocouple gives the reading more or less instantaneously. Reason is, the alcohol thermometer which we have used has a very high time constant of around 10 to 15 seconds, whereas the thermocouple is an electrical device. Its time constant is very small, a fraction of a second. So instantly it shows the reading. That is the advantage of the thing. So here you will decide which device to use for which measurement. If the temperature is rapidly changing, you have to use the device whose time constant is small. Whereas if the temperature is steady or the parameter to be measured is steady one, whichever you use, it doesn't matter. So for example, if you are taking the body temperature or a water temperature, in that case you can afford with a sluggish device like a mercury in glass thermometer or alcohol in glass thermometer, because here the time is not important for you and the temperature of that water is constant. But suppose you want to measure the temperature inside the chamber of a IC engine. IC engine, suppose if it is a 4-stroke engine, there are 4 strokes in 2 rotations of the crank, and the crank is rotating at a very high RPM of say 3000 RPM. So 3000 RPM means, that means 3000 divided by 60, that is 50 times a second it is rotating. So in 2 rotations, 4 cycles are there. So that means in 50 rotations per second, that is 1 upon 50, there is 2 upon 50 times the temperature in the things will change, because there are 4 strokes. For expansion stroke, the temperature is very high because the firing has already taken place. In compression stroke also the temperature is very high because you are compressing the gas. Whereas in the exhaust stroke and inlet stroke, the temperature is very low. So if you measure the temperature inside the IC engine cylinder, it is rapidly changing. And if you use thermometer for that, you will not get any reading at all. But if you use the device like a thermocouple, you can plot the graph, how the temperature is changing. You cannot measure that because it is so rapidly changing that your brain or your eyes cannot see it. But you can connect the output of the thermocouple to some oscilloscope or store the data in say some Excel sheet and then plot the graph from that Excel sheet. You can see the variations in the 4 different strokes of the IC engine. So now by this analysis, you come to know which device has to be used for which application. So this is what is the importance of the control engineering. So now thermometer is also temperature measuring device, thermocouple is also temperature measuring device, RTD resistance thermometer is also, the electrical resistance thermometer is also a temperature measuring device. There are thousands of different temperature measuring devices are there. Which device has to be employed where? Now that depends upon the response time of that particular device. Same thing is with the pressure measuring device also. You have a manometer, you have a Bourdon tube pressure gauge, you have a this what you call diaphragm type strain gauge mounted pressure sensors. So each one has different response times. So depending on your application, unless you analyze that, you will not know which one has to be used. If the data is changing fast, then it should have a low time constant. If the data is changing slowly, then you can afford to have a large time constant. No much error will be observed. So this is the response of the first order system. So the standard first order system response. So standard first order transfer function is k divided by Ts plus 1 when it is subjected to unit impulse input. Its output is k divided by t into e to the power minus t by t. This derivation you have to do. If it is subjected to unit step input, so unit step input transfer function is 1 upon s. If you multiply it by a first order system transfer function, then you have to use the partial fraction method and get this as output equation. C of t is equal to k into bracket 1 minus e to the power minus t by t. So this is how you have to do the derivation. So there are two derivations here, one for unit impulse input, one for unit step input. Similarly, there is for unit ramp input also. So first order system, how the effect of time constant. So smaller the time constant, faster the response. Blue is fastest and this is slowest because it has 7 seconds time constant, this has 5 seconds time constant, this has 3 seconds time constant, this has 1 second time constant. Lower the time constant, faster will be the response. K value. Higher the K value, more time is required to reach that. Here. Sorry, I made a mistake. K value has no effect on response. See here the time, this much time only, all have reached the same value. If K is 10, it will reach 10 in this much time, say 1 second. 5 also 1 second. 3 also 1 second. 1 also 1 second. That is because the time constant of the system is same, whatever it is. So the response depends upon not on the value of K, but it depends on the value of time constant capital T. This is not required. So we are not going to do this. In the next class, we can see the problems. Okay. So now I will take a break. Have you understood this? If you have any difficulty is there? If you have any difficulty, put it in the chat box or speak on the mic also.